Hi, I'm Jerry Stokely with ReefWorks, and today we want to talk about process control made easy. The whole secret to process control is contained in this big yellow box down at the bottom here with this ugly looking formula, and that's actually standard deviation. So we're going to estimate the population standard deviation, which is this O with a little tail on it, by using this formula. So let's look at this through an example. And before we start that, really want to talk about the bottom line. The bottom line is the output. It's the consistency of your product to your customer, consumer, what have you. And you get there by controlling the inputs. So understand and control your inputs to control your output. And we need a measure. We need to understand where we are in order to determine where we need to go. So let's take a look at a very simple example of a fundamental concept, and that is process control. So we'll use a slingshot as an example. That's something I think everybody can identify with. You probably played with one when you were a kid. So what do we want to do? We want to understand the inputs. And the inputs on a slingshot are the rubber band, the length of the rubber band, the condition of it, how you hold it. Are you pointing it down? Are you pointing it up? Is it level? How far do you pull it back in inches, millimeters, yards, meters, whatever you determine to be your distance measurement, the weight of the rock, and then the finger release in terms of milliseconds. The output here is the distance that the rock travels. So we're going to shoot the slingshot 10 times, and then we'll record each one of those as the distance traveled. Then that distance, we're going to calculate the standard deviation. It's very important to note that X denotes the distance traveled. So when we look at the chart, don't get too confused with that. So let's go ahead and look at our chart, and we shot our slingshot 10 times. And you'll see that here, shot number 1 through shot 10. The distance traveled, 300 inches or millimeters, whatever you want to call that, was our first shot. And then we go all the way down to the bottom here at 306. And if we add all these up and average them, we come up with 299.0. That's the symbol X. So we translate that distance to variable X, which is 300, 300, 252, 252, and so on, all the way down. Then we take the average and we place it in this column. Our first mathematical translation is to take the shot distance, X, minus the average, X bar. That's got that X with a little bar over the top. And you'll see that not all of these values are positive. Matter of fact, if you take these values, since we have the average, and you add them all up, you're going to get 0. So we need to understand what the distance is on the average basis from the average of all the shots. That'll make sense in just a little bit. So if we take the actual shot minus the average and then square that value, we'll end up with positive values. So X minus X bar squared is the second step in the process of calculating standard deviation. Then we go through all 10 and do each one individually, and then we come down to this ugly looking son of a gun here, and that big old E stands for the sum of X minus X bar squared. In this case, it's 43,480. Then we take the number of shots, which is N, minus 1. So we have 10 shots minus 1 equals 9. And then our next step is to take that sum of X minus X bar squared and divide it by N minus 1. So we're going to take the 43,480 and divide it by 9, and that ends up with 4831.11. Now, let's bring that down to values that are relational to our distances traveled. So we'll take the square root of that value. Remember, we squared them up here in order to make them positive. We're going to undo that by taking the square root. that's going to yield the standard deviation value. So here's our x bar, 299, and then we add one standard deviation, add two standard deviations. The standard deviation in this case is 69.506. And that gives us a spread from 90.481 to 507.519. Now, what do you do with those values? Well, it shows you what values are most likely. So we'll see that in just a second. It shows you the range. We just looked at the range here, 90 to 507. And it serves as a benchmark for where your process is so you can measure the effect of any change made to the process. And it all fits inside of this little thing right here, which you probably look at as I've heard it called the bell curve. It is a normal distribution. And the normal distribution is a statistical measure for where values are likely to land. So the middle is our average, 299. Then we go plus 1 standard deviation, plus 2 standard deviation, plus 3 standard deviations. Excuse me, those are the minus side. And the plus 1, plus 2, plus 3 over here. So you have negative 3 standard deviations to positive 3 standard deviations. And almost 100% of the values that you are likely to see under the normal conditions are going to occur in this range. So this value here is our lowest value, which is 90.481. And this value at plus 3 sigma is 507. So this is what's referred to as a 6 sigma normal distribution. So now you're probably thinking you could be a 6 sigma black belt. Well, that is the basis of this process. So let's go ahead and change the process and see what happens. Because this is all about making your process better. So let's change our process. And we'll do it very, very simply. And we took our slingshot, we just took a board, we drilled a hole in it, we dropped our slingshot into it, then added a couple of posts with a red piece of twine up here that represents how far back to pull it. So what happened? Well, what happened is this. We took, again, another 10 shots. Here's our distances for each shot, 325, 270, so forth. We came up with an average of 307, very close to our 299 of the last one. Variable x represents the distance traveled again, so we translate that here. Here's our average, 307.7. X minus x bar squared. Again, positive and negative values. You add them up, add all of these together, you're going to get 0. So we square them, x minus x bar squared. And you see those values here, they're all positive. We sum that, the sum of x minus x bar squared. Our next step is to divide that by n minus 1, which is this little formula right here. So we end up with 427.12, and then we take the square root of that 427 to bring it back to normalized values because we, again, squared it up here. So we're going to take the square root here, and that gives us 20.667. If you remember the last values, you know that's a lot lower than our first one. So now our range goes from a negative 3 sigma of 245 to a positive 3 sigma of 369.7. So let's take a look at this in a kind of a graphical format, if you will. So what was our net result? Well, here's trial 1, and 299 with a standard deviation of 69.506. And our process change, our average is fairly similar at 307.7, but our standard deviation is a lot lower at 20.667. So a reduction is 70.3%. Two simple changes, we made that reduction. Now, all these values are fictitious. They're meant to show you what can happen and the process of how to measure your process. So here's the distribution of our first shots. Up here, you can see it on this scatter diagram. Here's the average, right around 299. And the first value is 300, so that's represented here, second value, so forth. Now, when we changed the process, and you'll notice the charts are very similarly constructed, the very first thing you're going to see is this pattern is a lot tighter. So in essence, we get much more consistent results. And that's really what quality is all about, is consistency of results. So the secret to process control, and it really is easy, is to be patient. It's going to take a while. And begin at the beginning. Measure the consistency of your raw materials. Understand what they are. Break your process down into its major components. That could be bearings or adjusting screws. It could be pumps. It could be really whatever is in your process. Everything has some variation built into it. Measure your current state and calculate the standard deviation. This is going to serve as your baseline, and you can tell whether you've improved or disimproved. And most likely you're going to find something that is going to really change this process, and then you can brag on yourself and show everybody how good you did. So make small changes to the process. Small change, something like a bearing. Most every process has bearings in it. So, maybe that bearing's wearing a little bit and it's causing some variation. Measure the change state and calculate the standard deviation. Again, you really want to know, put down in hard terms, write it down somewhere where you can access it, because you're going to get called to meetings, you're going to have emergencies, you're going to, weekends, that kind of thing. You may forget what that number is. So write it down. Make sure that you can prove your work, if you will. And then compare your starting state to your change state. Just repeat it with one component after the other until you're satisfied with the results. And when you find that aha component, that one thing that really makes the big change, write it down. Let everybody know, and adjust your PMs and your work instructions to address that aha issue or that aha component. But don't assume that you're done. You want to come back periodically and remeasure to ensure that your work stayed on track. Because sometimes, if it's in a PM, it doesn't actually get done, but it gets checked anyway. So reality intrudes, and if you start seeing some variation in your process, go back to the beginning and remeasure. It's boring, but it makes a tremendous difference in your overall product quality and product acceptability as you move forward. And that can make a big change on your life and your success in life. So hope you enjoyed this. If you would like, send me an email. I'll be glad to send you a copy of the Excel spreadsheet. No charge, no problem. And if you have any questions on process control, feel free to email me. I'll get back to you just as soon as possible. Hope you enjoyed this. I hope it was useful for you. Please feel free to share this with anyone who you think might benefit from it. Have a great day, and we'll chat with you next time.